welcome back to our Gregorius Maths video. In this video we continue learning about algebraic geometry, and in particular we're going to be learning about algebraic sets, which is very closely related to the notion of an algebraic variety. And moreover, in the latter half of the video we're going to be looking at the Zariski topology as well, which is a very weird topology, which wouldn't satisfy some of the more normal conditions that you would want it to. But anyway, let's just, I don't see any reason to not start with just the definition of an algebraic set, so let's just write down this definition. So what the algebraic set does is it takes a subset of this ring of polynomials in n variables, and it will convert it into a subset of affine n space. So, given some s, a subset of k of x1 xn, we have that z of s is equal to the set of all points in an such that f of p equals 0 for all f in s. So it's basically the set of all points that vanish no matter which polynomial we pick in S. So, for example, some basic examples are z of 0 would be affine n space, because of course any point will vanish in the 0 polynomial. Z of 1 will be the empty set, because no points will vanish on the polynomial that sends everything to 1. And a single point will be z of x1 minus a1 up until xn minus an. That's just a1, an. Right, so, yeah, that's that. So those are some basic examples that hopefully kind of illuminate this definition. And these we'll be studying these algebraic sets in this video for sure, and in the next video we'll be looking at Hilbert's Nullensatz, which takes another operator which we call I, but we'll see it later, and what it does is instead of sending subsets of this to points in affine n space, it will send points in affine n space to subsets of this, and we'll study to what extent they're inverses, but that's in the next video. But my point is that these things will be quite important in our study, at least for early doors algebraic geometry. I'm not sure what's going to come next, because obviously I'm learning this as I go. I've only read a little bit ahead of this video. But okay, anyway, yeah. So, there's some examples. Now, our goal for this video is actually going to be to make these into a topology, but we have to deal with a technical issue first. So what exactly is this technical issue? Well, the problem is that so we can have two different sets S, and it won't change Z of S. So we kind of want to we definitely want to remedy that. So for example, if we have f in S and g in S, then throwing in f plus g, obviously it won't change anything, because, you know, they have to both be 0 anyway for them to be in Z of S. So that's one example. And if we have f in S and g in just some arbitrary polynomial, then throwing in fg also doesn't change anything. So these are some rather trivial examples, and what we're going to do is we're going to remedy this by instead of talking about Z of S, we're going to be talking about Z of the ideal generated by S, And what's convenient is that z of s by these two things and z of the ideal generated by s are the same thing anyway, so that's very convenient. So let's define this ideal. So the ideal generated by s, which we denote like this, is the set of all f1 g1 plus up until fn gn, such that fi, so all of the f's are in s and all of the g's are in r, but in this case it's just k of x1 until xn. And immediately note that z of the ideal generated by s is simply the z of s by these two notes here. So it doesn't change anything in that regard. It's just a technical issue that we can easily get over. A not so easy issue to get over, which we will look at in the next video, is the fact that even though the two ideals, for example x1 squared and just x1, these two ideals are not the same, yet z of x1 squared and z of x1, they're the same. So we need to remedy that, but we'll do that in the next video. I just want to flag that up as a little issue that we still haven't solved yet. Okay, but now that we've done this, what we're going to move on to is we're going to show a little lemma which might look familiar from topology actually. From very, very elementary topology. Like, this is nothing advanced in topology. In fact, this will look very familiar if you know the definition of a topological space. So, let's just state the lemma. Firstly, we have these two things, which we should really be putting in this lemma, but you know what, it's fine, we'll just leave that detail up for now. Firstly, we have that first one is given just a family of sets Si. We have that the intersection over all I of z of Si is equal to z of the union over all I of z of Si. Okay, so that's the first lemma. And second part of this lemma is okay, if we have S1 and S2, basically we have Z of S1 union Z of S2 is equal to Z of S1 times S2. Okay, so unions of finite unions are closed, and part 3, which isn't part of the definition of a topology but it's another useful one to know, is that if we have S1 subset of S2 subset of K of x1 xn, then Z of S2 is a subset of Z of S1 is a subset of an. So, okay, so hopefully this and that, after thinking about it for a little bit of time, are obvious. For example, for this one, 0, this 0 here, I mean that's yeah, for example for this one, if we have the 0 polynomial, and then we have another set which is the 0 polynomial and just some arbitrary polynomial, then obviously the set containing the 0 polynomial is going to be a subset of that other set. However, Z of 0 is the whole space, whereas Z of that other set will just be the set of zeros for that one polynomial f. So that's kind of like a little example to explain the reasoning behind this. And for this one, again, if you just think about it for a little bit, then it should become somewhat obvious. It's definitely somewhat intuitive that the more sets you add on inside, then the more you're taking away from this. But you know, it's just, yeah, hopefully after thinking about that one for a while, you can get why that one is true as well. But number 2 I will prove here. So I'm just going to do a good old classic thing where you prove that this is a subset of that, and then you prove that that is a subset of that. So, okay, so let's prove this first. Okay, so let P be an element of this union. What we want to show is that P is also in this set here. So P is in here. What does this mean? This means that either F1 of P is equal to 0, or F2 of P is equal to 0, where F1 is any polynomial in S1, and F2 is any polynomial in S2. But therefore, when we just multiply them together, we get thus F1, F2 of P is equal to 0, and so P is also an element of Z of S1, S2. So that's a nice little proof for that direction. Now for the other direction, what we're going to do is we're going to assume that P is not in this union, and we're going to show that P is definitely not in here as well. And the reasoning goes pretty much in exactly the same way. Now that I sit down, I can see how slanted the writing gets, especially on this side, but I can only apologise for that. Yeah, okay, anyway. Alright, so for the other direction, let's assume that P is not an element of this union. Then there exists F1 and F2 in S1 and S2 respectively, such that F1 of P is not equal to 0 and F2 of P is not equal to 0. Therefore, when we multiply them together, F1, F2 of P is also not equal to 0, which therefore means that P is not in this set either. QED. Okay, so that's, again, this is just another satisfying little proof there. So, okay, now that we've gotten that out of the way, this should remind you of closed sets in a topological space. We also have these two. So, we are well within our rights to define definition the Zariski. Pretty sure this is named after the guy who actually came up with the topology, but because I do know that Zariski was definitely a mathematician, but I couldn't say for sure, but that would be my very strong guess. The Zariski topology on AN is given by closed sets being algebraic sets. And we just proved in the previous lemma that this is indeed a topology. So, just to round off this video, I want to just hammer home how weird this bloody topology is, because this topology is really weird. So, for example, any closed subset of AN has dimension less than n. So closed subsets are really tiny, basically, which also means, I'm not sure if this is direct implication, so I won't write that, but the intuition is closed sets are so small, that means that open sets are really massive, and basically it's not Hausdorff. I think it's with double F, not sure. Looks wrong with double F, I'll just say. Not Hausdorff. If we just restrict ourselves for a moment to A1, in A1, all finite set, so the closed sets all the finite subsets of A1, and so any bijection F between A1 and A1 is a homeomorphism. I'll put a little exclamation mark. I'll even put the exclamation mark in red to really emphasize that point. So this topology is super out of the ordinary. It's nothing. It's got none of the properties that one would expect. Super weird. And this last thing here, this is a hint. Not to make morphisms between varieties have to be continuous underneath this Zariski topology, and actually we'll look at how to define morphisms between varieties in a few videos time. That's not coming up too soon. What is coming next is Hilbert's Nullenstats, where we will examine, as I said, a function, we'll call it. Don't really want to call it a function, but we'll call it a function I, which sends points in AN, two ideals in K of x1 and blah 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 until xn, whereas this one sends ideals to points in AN, if that makes sense. So, and then we'll study to what extent they are inverses. Anyway, thank you guys for watching this video. Hopefully you learnt a little bit about algebraic sets. Notice that it only took me a week to upload this since the last video, so, you know, hopefully that's a sign of, you know, weekly uploads, but not promising anything. I wanted to do 2 a week, but 2 a week is kind of difficult, but, you know, if I can do 2 a week, that would be pretty cool. But anyway, let me just fix this. Yeah, okay. Anyway, yeah, I'll see you guys in the next video. Bye.